also built other tools that fall on different parts of the spectrum. So for example, in our recent Usenix 24 paper, we described a technique that constructs this graph abstraction of ZK circuits and does analysis at the graph level. And that's a much faster technique. It doesn't require any SMT solver support, but it doesn't have any guarantees. It can have false positives, it can have false negatives. We also looked at the technique all the way on the other side of the spectrum. So we actually have this programming language for ZK circuits called CODA, and it uses a refinement type system, and then it basically, when it does type checking, it will output a bunch of Koch lemmas. So this technique is actually not fully automated. It can verify full functional correctness, but in the case where the built-in Koch tactics fail, a person needs to go and prove those Koch lemmas by hand. So this is not fully automated. And there are a bunch of future directions that we're interested in exploring that some of them we already started on. Someone was asking about those. So one thing I'm very excited about is, like I said, a lot of our work has been focused on SERCOM and R1CS at the low-level representation. But there are constantly emerging DSLs for implementing ZK circuits, so we're interested in building a verification-friendly intermediate representation for ZK circuits that can support many different languages like NARC, Halo 2, SERCOM, and others. Another thing that I'm very excited about is specialized solvers for integers plus finite fields. And why am I excited about that? Because if you want to prove equivalence between computation and the circuit, all the circuit constraints are in finite fields, but all the computation use integers. So if you want to reason in an automated way about equivalence, then you definitely need good SMT solver support for theory of integers plus finite fields. And currently, we're also looking at more automated techniques that use SMT solvers for verifying equivalence between ZK circuits and the computation they encode that don't rely on manual proofs using Koch or Lean or some other interactive theorem prover.